For your information. So we will actually put not only the presentations but also the recordings online. So we have arrived at the second talk for this session, and I'm pleased to introduce Chris Hobbs from QNX Software Systems. Software defenses. We look forward to that. Welcome.
Thank you very much. Thank you, everyone. Yes. Before we dive into what I really want to talk about today, I'd just like to upset a few of you with some of an idea that I've got to start with, I think. Random software errors. These have sort of been touched on today in Peter Ladkin's talk, where we spoke about systematic capability rather than random errors. I am going to be mentioning, as we go through this presentation, I'm going to be talking about random software errors as well as random hardware errors. So I know this upsets a lot of people. It's caused all sorts of storms on the internet when I publish stuff about this. Most of the safety standards, as it says there, assume that hardware errors can be random and software errors are systematic, and we deal with them with systematic capability. I believe that is complete rubbish. Mechanical hardware errors do appear to be random because we do not know the position of all the molecules, the energy of the molecules, where the molecules in that mechanical system are. And even if we did, we don't have enough processing power in order to work out what's going to happen next. QNX produces an operating system. I estimate that it has something like 10 to the 300 states. There are 10 to the 80 nucleons in the universe. So we are well beyond anything that you're likely to get. There's just not enough nucleons in the universe, as we already heard about once today. Anybody like to come up in a break? I've got a 33-line C program that fails. It's completely random when it fails, but it's about every 300 million times it's run. And it's a very simple little program of the sort that anybody might write. So it normally takes about 20 minutes to fail if I run it on my machine. Okay, so that's just introduction. Let's go forward from there. What I want to talk about are two problems and a potential solution to both those problems. The first problem that we are all meeting, I'm sure, in the industry, has been pointed out several times today already, that software by itself cannot be unsafe. It needs hardware to run on, and we know that the hardware is becoming less and less reliable. As tracking reduces in size, I see that we now have a new 10 nanometer chip coming out this week. So yes, that's becoming less reliable. And we have two aspects of system design that we'll be talking about that are becoming increasingly complex. And I want to try to pull these apart. So let's just look at the first problem. I think it's something that we're probably all very familiar with. Most modern processors come with more than 20 pages of errata. There was one I saw the other day on a very famous processor that's being used in a lot of safety-critical systems. Sometimes instructions are executed out of sequence. Workaround, none. On a safety-critical system. Secondly, we have what we know about cosmic rays, electromagnetic interference, and to bring this presentation up to date, I noticed last Thursday from the Vrije Universiteit in Amsterdam, they were demonstrating how you can actually induce row hammering problems from a browser, with a JavaScript in a browser. So suddenly row hammering, which was the crosstalk between rows and columns in the DRAM, is now easily exploitable. It was exploitable. You can now exploit it with JavaScript. They did it on 2 different browsers. That was published last Thursday, I saw. And of course, multi-threaded applications, particularly when they're running on multi-core processors, do introduce random software errors. Random software errors, those 3 words that come together. According to the Google paper, DRAM in the wild, we can expect about 25,000 to 70,000 bit flips per 10 to the 9 hours per megabit. What does that mean? Well, it means if you've got a 2 gig dedicated system, then you can expect a bit flip about every hour or so in your memory. Nice quote from Rob Ashmore at the conference in Bristol back last year. All software running on a modern microprocessor is non-deterministic, which I think is an interesting quotation. So what does this mean? If we're going to have a bit flip every hour or so on our embedded systems, what does it mean? Well, what it means basically is we can no longer go to our design safe state every time we have a hardware error. Because if we did, we would have cars, trains, stationary all over Europe, all over North America. We've got to do something else. Okay, let's look at the second problem. There are thinking particularly in terms of automobiles, but this could also be any of the other systems that we deal with. There are 2 parts now that are becoming clearly distinct. There is the calculation of the safety critical data. We're on a wet road going uphill at X kilometers an hour. There's another car in front of us, this distance from us, X meters from us, and what have you. What force should we apply to the brakes? So the computation of that, the fact that we should apply 450.3 newtons, is a sophisticated computation. There is also, hold that for a second, because there's also the question of the availability, reliability, balance of the system, the dependability of the system. These are skills determining whether we should have a 1 out of 3 system or 2 out of 3 voting, or we should have a disparate system with a safety bag type technique. These are 2 different aspects of the same system. One of them requires quite a high level of mathematical competence to do those control loop computations and what have you. The other requires a significant amount of statistical analysis and statistical background. It's unreasonable to require these to be coming from the same designer in a large extent. So, conflating those 2 problems, how many newtons force should I apply to the brakes? And I'm doing this at the moment, I'm on a highway, I'm on a motorway, I'm on an autobahn, I'm in the city center or whatever. What level of dependability do I need? If we conflate those 2 problems, we make the design too difficult for anybody to do, and it leads to complexity. If we can pull them apart, then it is going to improve both our verification and our validation, I believe. So, I believe the questions that we have traditionally asked in the safety critical industry are changing. And as you can see, I have a white beard. I've been doing this for a while, and I've seen these questions change several times. I think we're on the point of this one changing. So in the past, we have asked ourselves, has a hardware error occurred? Because if a hardware error occurred, a bit flip has occurred, or a register has become corrupt or something, we've got to move to our design safe state. I believe that is no longer the appropriate question. In fact, it's no longer a question that is of real interest to us. They occur too often. If you're having a bit flip every hour, then you can't stop the train every hour. You can't stop the car. You certainly can't stop the aeroplane every hour to do something about it. Because most of those bit flips are not going to cause a problem to our safety system. They're in unused memory, they're in bits of memory that have just, it's not going to affect the safety function of the system. So I think today's important question is not, has a random hardware error occurred, or a random software error occurred for that matter, but has something happened that has negatively affected our system? That's the thing. So it's an obvious question, and can we ignore hardware errors? Do we actually want reports of hardware errors anymore? And for statistical purposes, clearly yes. I mean, that Google paper does point out that the more the fact that a bit flip occurred today in that particular DRAM increases the probability that there will be a bit flip tomorrow. So yes, for statistical purposes, I think this is useful information. For making decisions about what to do with this safety critical system, I don't believe that's the fact that a hardware error has occurred is useful information anymore. Okay, the second question. How can we build the required dependability into this application? And by dependability, I include reliability and availability. I sort of conflate those into dependability. I think, again, that is the wrong question. The dependability has to become independent of the application. So I think the important question today is, how can we separate the design of the application, the fact that I have to apply 126 or whatever it was, newtons of force to my brake pedals, from what aspect of design, dependability? Am I looking for 3 out of 4 voting? Am I looking for 2 out of 3 voting? What's my level of dependability that I'm going to need? These things have got to be separated, I believe. So, I'm going to be talking about lockstep, but I'm not going to be talking about hardware lockstep. There are processors, as we know, that have hardware lockstep, that basically do the same computation in 2 processors simultaneously. I believe that is inadequate, very inadequate. In the first case, the number of replicas that I can have on my hardware lockstep processor is normally determined by the hardware. So I can't change it very much. It may be 2, it may be 4, but it's a fixed number, which means I cannot balance my availability and my reliability dynamically. It's fixed. It's what I've got from the hardware. Secondly, I cannot build my system around diverse implementations. The hardware lockstep implies that both, or let's say there's 2 for a moment, that both of the systems are identical because they're going to be executing identically. So I can't have diverse systems. It only supports replicas. And it doesn't defend, the hardware lockstep doesn't defend against my random software errors. So basically, Heisenbugs, the random software errors that are going to occur, are going to hit both, all 4 or whatever, hardware lockstep processors simultaneously. It's end of story. So in what I'm going to talk about now, there's a couple of reference architectures that I'm using. I'm making the assumption that all embedded systems are one of these. So let's look at the top one. We have some sensors on one side. We have a calculation engine doing some form of calculation. What pressure should I apply to the brakes? What should I start braking now? And it drives some actuators. I don't think there's much of interest there. That's what all of our embedded systems, I think, do. One point I have made here, for those of you familiar with ISO 26262, is I have made the assumption from the experience I've come from with lots of our customers, is that it is going to be very difficult, at least, and probably impossible, to claim any form of ASIL level certification for that software. It is highly complex, it's very difficult. Now, it is amenable, I think, to the formal methods approach much more than other types of software, but even so, I believe we're probably going to be claiming that to be quality, QM, quality management type software. We will have possibly some form of monitor which has been developed in accordance with an ASIL, monitoring it. Monitoring the inputs, monitoring the outputs, monitoring the behavior of the system itself, and this is, of course, much, 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 much simpler than that. And what the monitor is saying is, I'm not as clever as my friend up there, but given those inputs, there is no way those outputs are safe. I am going to override my intelligent friend. I'm just a dumb friend. I'm going to override my intelligent friend and do something, possibly pressing the reset button, possibly whatever. The bottom one is very similar, except here the monitor is sitting in line, and what it's doing is it's saying, well, given those inputs, those outputs are unsafe. I will replace them with known to be safe values, or I will press the reset button. So that's the problem. So that's the reference architectures, one or other of those, doesn't matter which one. So a road towards a solution. We would like to detect errors, and that's detecting the errors is often the hardest part of it, whether they're software or hardware, that affect the system. Now, since actually the late 1980s, the data storage industry has been using virtual synchrony to solve this type of thing. Not safety critical in their case, but mission critical. So what we've done within QNX is went down to see Ken Berman down at Cornell University, who's been working on virtual synchrony since the late 1980s. I'm glad in a way I'm not an academic that has to work on the same problem for 40 years, but and to explore this question, could the virtual synchrony model that's been used in data processing work in our embedded world? It wasn't built for our embedded world. It's a very different world, the storage world, where state is measured in terabytes rather than kilobytes, where systems are much bigger, much more distributed over LANs or even wide area networks, and so on. Whereas we have possibly buses between processors, cores, or worse, backplanes. But, okay, can it work? So what is virtual synchrony, for those who may not be familiar with it? Is anybody not familiar with virtual synchrony? Okay, there's some hand. Oh, good, great. Okay, that's what I like to see. Okay, so the idea of virtual synchrony came out in, as I say, the late 1980s. I was working with it in the storage industry in about the early 80s, I suppose. Early 90s, I suppose I was working. Early 90s, that's right. So the idea is this. We take, here is a server of some sort that does something. It provides a service. Here is a client that wants to get service from that server. What I would like to do is, I would like to be able to replicate or diversify that computation engine, and for the client not to know anything about it. The client still believes that it is talking to a single server. The single server also doesn't know that it's a member of a group. The server simply responds to the client requests in the way it would. So the nice thing about this is minimal change to the client, minimal change to the server. We've actually got it, so you have to call an initialization function, which is a bit annoying, but that's all we get it down to. So the idea here is that something in the middle is doing all the magic, and it's providing a single guarantee to the system, is that all messages from the clients, and of course there'll be multiple clients acting independently, all events, in fact, and all messages from the clients in particular, will be delivered to all instances of the server in exactly the same order. That seems a very easy guarantee to give. Actually, it is incredibly sophisticated, particularly when these things are failing, and some of them have received information that the others haven't, some of them have responded, which is that others haven't, and so on. So as far as the client is concerned, the client sends a message to what it believes is a single server. It can ask for a single message back, a single response back, which the middleware can provide, or if it wanted to know that it was connected to a bunch of servers, it can ask for all of them and do the comparison. So this is the virtual synchrony mechanism. And there's a lot more detail, obviously, we could go into on that, but that's basically how it works. So what does this mean for our embedded industry, and in particular for the safety critical world? Ken Berman, who was the sort of father of this, along with Robert Furness and people, wrote back in 1987, in a virtually synchronous environment, routines will behave as if distributed actions were performed instantaneously and in lockstep. It will appear to any observer, anybody on the outside, that the process is in lockstep. In fact, it is not in lockstep. That's the important point. So it doesn't suffer from the same disadvantages that the hardware lockstep suffers from. So in this picture here, we could have this running on one processor, this running on a different processor, along with that one, and so on. Given the trouble we have of keeping things in lockstep, it doesn't take much to get them out of lockstep, which is what we actually want. We want them to be out of lockstep. So we call this loosely coupled lockstep. A couple of other organizations have stolen our term, which is really good. That's what I like to see. So what can we now do? Well, first of all, we can now move this balance, this important balance between availability and reliability. If we are zooming down the Autobahn at 220 kilometers an hour, availability may be more important to us than reliability. There's not much I can do with that car at 220 kilometers an hour that is particularly safe anyway. And I'm not expecting to see children running out ahead of me, or nuns shepherding orphans, or whatever the normal problem is. However, once I get into the city centre, now reliability may be much more important. It is important that I recognise whether that is a raccoon running across the road or a child. It's important to know whether, whether I've got to stop or not, and whether it would be more dangerous to stop or not to stop. So here on the motorway, I might take 2 out of 3 as an availability. Once I get into the city centre, I might want 3 out of 3 and have one of those monitors sitting on my system to ensure that what the answers I'm getting are the correct answers. So the loosely coupled lockstep implementation, as I've said before, in the simplest case, the client does not know it's talking to multiple servers. The server does not know it's interacting with multiple clients. That's all taken care of in the middleware. So we want to make as few changes as possible. This is particularly important if we think about that second problem. The mathematician who is doing all of that computation to deduce that we should put a force of 36 newtons on the brake pedal should not be involved with this type of 3 out of 4, 3 out of 4 with monitor, 2 out of 3, or whatever. That should be independent. We should not need to change that application in order to move it into this environment. We should be able to move dynamically between availability and reliability, and we should have complete independence of the server. The argument, of course, is, the underlying argument of this is that given that I've got multiple copies of this, the probability that I will have the same problem on every instance is very low. It's the same Heisenbug occurring. Heisenbugs are caused by race conditions. The chances of having the same race condition in 2 or more processors is very unlikely. If it were likely, it's not a race condition, it's a ball bug, and it should be fixed. So here is an implementation. We have some communication channels. The little yellow blobs are the libraries, a server library and a client library. And you link your process with the library. The yellow magic basically replicates all of these sensors are sending information asynchronously. The actuators are demanding resources asynchronously. Those are being delivered in order to all of the QM programs and to the ASIL monitors in line and in the same order. That's the guarantee. The guarantee then underlies the principle that if all of these servers, the calculation engines, are starting in the same state, and that's taken care of by the yellow blobs as well, if they have received exactly the same events in exactly the same order, albeit at different times, then the system must stay synchronized. I didn't believe that when I first started using this software, but after a while, I've become more confident. So what does this mean in, say, an automotive application? Well, on the left there, we have a number of sensors. Downward-facing radar, wheel rotation, GPS, inertial navigation, maps, and so on. We would then presumably have a sensor fusion layer, one of which will be determining speed, one of which might be determining location, one of which might be determining all sorts of things. Taking the best values we have from the sensors, doing the computation, and passing them on to speed control computation, direction computation, and so on and so forth. We would like, for benefits of dependability, to replicate or have diverse implementations. And by diverse implementations, I mean it could be simple as using a different compiler, or different compiler options, -02 instead of -03 or something like that. It could be more sophisticated. It could be a fully developed different team of people producing it. But these are going to act as a single entity. The GPS, for example, is talking to a single entity, or believes it is. It's being replicated by that yellow magic. Those are then talking as a single entity to the computation engines. The brakes are then requesting, can be pull or push, requesting what pressure should I put on the brake pedal now, what should I put on the accelerator, and so on. So, we have tried this out. We've tried it out on several systems. We've been to Los Alamos and put it in a nuclear reactor with lots of neutrons firing at it, which was interesting. The results we got were not exactly what we expected. We've been to the Los Alamos reactor twice, got a lot of useful data out of the first run. We didn't get as much useful data out of the second run because we were the first board. I don't know if you know how they do it. There's a neutron beam is coming out of the reactor, and they have then a number of boards, number of experiments that are being carried out. On the second time, we were the first board, so we had the full impact of that neutron stream. Our system was staying up at all for an average of about 3 seconds every time we ran it. The first run, we were further back in the stream, and we were staying up for sort of 3 or 4 minutes at a time, and that got us a lot more useful information from it. So, and it seems to work, is the good news, that we can dynamically change the availability, reliability balance, and we can isolate the computation from the statistical analysis of the dependability of the system. So, software is subject to random hardware and software errors. As we said earlier, the software can only run on hardware, so I think of that as the software being susceptible to those random hardware errors. Some of those we know are in the errata. The processor sometimes executes instructions out of sequence, workaround none. But the race conditions that we are seeing are manifesting themselves, I believe, purely as random software errors. And we've got to accept that, or at least I've got to accept that. You don't have to accept that. The most important questions now are not, have we had a hardware or software error, but has anything happened that has affected the safety functions of my system? The loosely coupled lockstep architecture based on the virtual synchrony algorithms, which, by the way, have been formally proven by the people down at Cornell, addresses this question, I believe. It provides only virtual synchrony. That is, as we saw in that quote from Ken Berman, from the outside it appears to be running in synchronous lockstep. Actually, it is not running in synchronous lockstep. So it can defend itself against both hardware and software errors. The hardware lockstep cannot protect us against software errors. And it does cleanly divide those two areas of expertise, the mathematical functionality and the statistical balance. That's it. So thank you very much.
We do have time for a couple of questions. Peter.
Peter.
I have two. The first one is, what's on the other?
Yes, the 300, I put this here because this 384, because I like to frighten people, particularly when I'm at a customer meeting. And yes, these are latex slides, and I can never find the way of suppressing that, so I thought the better way of doing it was simply to put a number in that would just frighten people. So that's...
The second question, which may be a little bit more substantial, is why do you think neutrons are the problem? Boeing Rad Lab was interested in neutrons in the 90s because they thought most DRAM problems in aviation were being caused by neutrons. It's what they claimed. They actually concluded that because they went to the same accelerator you went to, and they put DRAMs in the accelerator. The problem is they got a statistically significant asynchrony in the flips of the bits, which shouldn't occur with neutrons, but they seem to ignore that in the paper they wrote and just said, we proved it's neutrons. Why are you most worried about neutrons rather than muons, for example?
Yes, the answer to that is I am not a nuclear physicist. This is the picture that we've been using, and yes, muons are on there. Whether it is neutrons or muons or whatever, honestly, I don't know. We are told that it is neutrons as a secondary effect of cosmic rays, but whether it is or not, I don't know. Certainly the neutrons did cause bit flips, and what you say is interesting because they did not cause bit flips in the way we would imagine they were going to. So maybe we have suppressed a bit of research as well, because that wasn't what we were looking for. We were just looking for the bit flips, and yes, interesting. I will research that.
Okay. Any further question? Yes?
On your experience, what's the complexity of that middleware element and the magic that you talk about in the virtual synchrony?
Yes, I think the complexity of the middleware, the complexity of the magic, the yellow magic. There are lots of algorithms out there. It's not just the virtual synchrony algorithms that do this sort of thing. The various universities over the world, and there's Leslie Lamport with his algorithms and so on, have come up with these algorithms. We chose virtual synchrony because I was familiar with it, and it's the one that I worked with in the mid-90s. The coding is extremely subtle, but the good news is it has been done, certainly for the storage environment, by the universities and proven to be correct. So yes, it is subtle, but no, you're not starting with a blank sheet of paper in general.
Okay.
John had one up there.
Final. Okay, hang on.
Chris, just hopefully this will work. Chris, there was a comment about neutrons. It may be worth looking. Rockwell Collins have a bunch of patents on logic that's immune to single event upset, which arises out of their experience of failure modes of avionics, flight management systems, and so on. And that might give you some other ideas of the type of failure modes these things are affected by, and what can be done at the hardware level to deal with them. The patents are quite old now, but I think the underlying logic still applies.
Right.
Okay.
Yes, thanks.
Thank you. I just have a last question. I can't resist it. On your first slide for the Swedish audience here, you had a very challenging English word, something like Prolegomenon. Would you care to teach us how to use that?
So any other native English speaker here would like to explain the origin of this word?
I think it's Greek.
Yeah.
Actually, isn't it? So I don't speak Greek.
Yes, it's introduction, it just means introduction. And I just wanted to confuse people even more. Yes. It just means introduction.
Okay, thanks a lot, John. Very interesting.
Thank you. Thank you.
Many people here. Hope you don't leave now before the lunch. So I will talk about a research project that I am running called SMILE, and it's safety analysis and verification validation of machine learning-based systems. So we're looking on how to use machine learning in safety-critical systems. And this project is funded by FFI, and QR Tech, Volvo Cars, Volvo Trucks, Semcon, and RISE, and that is RISE Victoria, where I work, and also RISE 6 in Lund, are parts of this project. And it started in October and ends in October 2019. So why do we need machine learning in vehicles? That's maybe a good question, especially in this room. So traditional rule-based methods are quite static. They are rule-based, but neural networks have the ability to generalize, to take new decisions that are in line with what they have been trained for, but they are not rules then. And right now, there are some trends that makes it possible to use machine learning. So a couple of years back, developments in neural networks, or then deep learning, which is the technique we use, was that they started to be very accurate compared to traditional neural networks. And then also computational power. There are companies now that provide dedicated hardware to do training of these networks and also execution in vehicles. I don't know how familiar you are with machine learning, but in the area of artificial intelligence, it's a quite big area. And in that, there is machine learning, and then a very small part is these technologies that we call deep learning. So what are the challenges then? We don't use this waterfall approach. We don't write any specification, but we use the training data to define what the network should know about. So it should learn from historical data. And we want the network to generalize. So even though an object that looks like a car that was not in the training data, it should anyway be classified as a car. The problem then is what we can see here. A neural network is trained to recognize this image as a panda. And it says that, yes, it's with almost 60% confidence, this is a panda. But then you can add noise from this panda, and you only add very, very, very little noise, 0.07 times that noise. And that noise itself looks like a nematode. Very small confidence, though, 8.2 confidence. But when you add these two together, the trained neural network thinks with some high confidence that this is a gibbon. So I'm not saying that this is very likely to happen. You have to know exactly how the neural network is built up to be able to create this noise. But if you have the access to the network, you could probably manipulate the network in such a way. So deep technologies are, when I did my PhD, I used one hidden layer, and then it was deep technologies, and I think just the definition is more than one layer, so it's not very much more complicated than 10, 15 years ago, but they have special features and properties. So here are 2 examples I found on the internet. The first one is about adding these input signals to a polynomial. So you can, with these products and sums, you can create a complicated function. Let's see if this works. So it consists of this, for example, x2, x3. It can be in many different places in this function. So it can relate input data in different ways, depending on how you design this network. So this is an equation. Maybe it's more simple to see it here in this text example, where this news says that United Airlines fell 8% yesterday. That's a fact from the news feed. Another fact, United Airlines suffered from bad publicity. And then Ford lost 3% because of bad publicity. So the network can relate these things and possibly create new knowledge, saying that United Airlines fell 8%, possibly because of bad publicity. So it can understand in a sequence what are the interesting things. Otherwise, typically, you just look at the scene and you classify it. But with deep learning, you can also add like a time aspect or a sequence understanding. So you can relate things that are not it's not evident that they belong together. Okay, so be able to use these networks in a car, in an automated vehicle. We heard before that the use case or the area of where this functionality is going to work is very important. So in an automated car, it's very good to know what is the role of the driver that is then getting help from the neural network. And then what is the role of the system? This ODD, Operation Design Domain. So where should this system work? So right now, we see that the vehicle OEMs, they make a lot of effort is brought in confined areas, for example, where there are no humans. So you can narrow the scope a lot, and you can learn about what are the problems and how does it work, and there is not so much harm to any humans there. Drive Me, for example, Volvo Cars project, that is running on even though it's in real traffic, all roads are 70 kilometers per hour, and there are no pedestrians and there are no traffic lights. So already these machine learning techniques are used, and they are also used in a very narrow domain. So for us, we think that to be able to do automated vehicles, we need to have neural networks for perception to understand what is the scene about. And we want to train these networks to understand dangerous situations and also anticipate unforeseen situations. So just to give a little background here, we found a good paper that summarizes the ideas that we have in SMILE. There are 5 areas where machine learning impacts on ISO standard. So I will go through them here. So about identifying hazards. So in these systems, like adaptive cruise control, automated braking, and so on, the automation takes over more and more. And Drive Me, for example, the cars should be able to drive by themselves. That means that the driver is released from this burden to drive, and in some years, the driver may not be able to take over, and especially when the system fails in difficult situations where the driver definitely don't have any training anymore. So this is a hazard that may not exist today, but may exist in the future. So we have to understand this complex behavior between the vehicle and the driver, and those can be things that should be taken care of in the standard. There are faults and failure modes. We heard a lot about that before. The system gives an incorrect output, but that it shouldn't. But there are current standards and rules and ways to handle this. So this is not particular specific for machine learning. As I said, we use a training set to define the functionality of these systems instead of the specification. So you are out driving, collecting data, maybe simulation to generate data, but there is no way to obtain all possible scenarios, not even in a very simple confined area or a simple 70 kilometers per hour road. There may always be things that occur that are not in the training data. So we have to design our systems to be able to handle these errors that can occur. And also the level of machine learning, it's easy to think that I can put in a neural network that takes in the radar and the camera, finds all the obstacles and is able to navigate, and gives that the neural network gives the output to the car, what steering angle and what speed. But in the standard, you want the system to be clear, and it should be able to have a good overview of the system and how the components are working. And that is definitely not the case if you make such end-to-end system that is capable of handling everything. It defines both the architecture and the software and the functionality. And if you train your system with the same data twice, the architecture of such a system will not be the same, not exactly the same at least. So when we use machine learning in these systems, they should be small and at the component level to be able to test and monitor, and not to be big black boxes, but small black boxes. Then there are lots of software techniques. I don't know how many, but very many, and they are quite explicit and defines how the code should be written. For example, you should have good variable names so that you can understand what this variable is all about. But this doesn't make sense in machine learning because you don't have much variables. So instead, you should express these requirements in terms of intent, and it should define the usage or the purpose of this variable instead of defining how it should be done. Okay, so in the SMILE project then, we accept that these are black boxes, but we need them for perception. And we are going to build a camera-based perception model that we would like to test to see how it works when unforeseen data are coming in. So that's one thing. We also want to look into how pre-training works. As I said, the neural network is trained with historical data. And they are inspired by how humans work, how our brain work, because we also learn from historical data, and the small elements in the neural networks are similar to the one in the brain. And when we start driving the car, we have been living for 16 years and learned a lot of things, what is dangerous, what is not. So when we start putting ourselves in the car, we have a lot of knowledge before we start driving. So is it possible to also use data from other domains than just this 70 kilometers per hour road, where there is only a road and cars? Possibly it would improve quality of the methods. So we want to look into that. Another thing is how this, we saw this risk slide before from Anna, that you learn from accidents, then you know that it's a risk. And it's the same here. We start out with all the data that we have, but we want to learn more and more things over time. So how can we handle these model updates and also look into how they can be verified and tested with new data and so on. And we want to demonstrate, of course, our use case. This is very difficult, so we should start training our system at a summer road, and we want to test it to see if it can handle a winter road. But we hope we can do that at least. So SMILE is about building a safety cage to monitor the data that is presented to the network, very similar to what we saw in the previous presentation. And what the network is doing, it's actually, this is a typical design of a convolutional neural network that makes classification. So you input images here from your camera system in the car, and the system learns, it's called features. Here are some features from faces and from cars. So in this initial layers, the network learns shapes. Here are, for example, lines, derivative filters probably, that are implemented here in the nodes. And together, these filters are combined to create an eye, a nose, a mouth. And then it combines more of them together to make the face. And it's similar with the cars. So what we want to do is to use this kind of model in here. But we want to make sure that when something unforeseen appears here on the input, we want to take a safe track instead. But the new thing here is with images, video images. How do you separate a known image from an unknown image without using this neural network? And we have been looking into that. So we have made some initial work on autoencoders. Autoencoders are also neural networks, and they are trained to take the input image and compress it into some distinct features or special features on a low dimension space. So these are input images are very high dimension. It's 1,000 by 1,000 pixels in a HD image, and then it's color images, so it's 3 layers, and each layer maybe 255 grayscale levels. So it's a huge input space. And then we want to compress it to some smaller space and then decode that compressed space into a learned representation. And we think that when we present the training data to this system, the known data, it should learn the known representations or the known way to compress the data and the known way to decompress. And we could then compare the input original image with a learned representation. And if we are in the known space, we think that this error will be small. So that is what we have been trying to do with some really simple data sets first start out with. And it's MNIST, it's a lot of numbers and letters. So we say that we want to learn these numbers, and then we should recognize these other figures that are not numbers, so that we can raise the alarm and say that, hey, don't use this in your model. So some basic procedures then to do that. We need to resize the data from the two databases are not the same, so we need to resize them. And we used two different approaches to just to take the large image to a small image. So nearest neighbor and bilinear interpolation. These are the red one here is the decoding and then or encoding and then decoding up to the learned representation. And this is an example of how it looks like on the inside and on the outside. So it learns pretty well. Here is some missing, but it learns to do this. And here are some examples from how we did it. So there are thousands of images of each number. And this is the reconstruction error from the histogram of the reconstruction error of all the zeros that we did, and the ones and up to 9. So how big was the reconstruction error? And then we looked at this thing. How can we reconstruct that? What is the error of the reconstruction? And we see that all these are quite low. It's around 1.5, and here it's above 2. So when we look at this, depending on where we take the decision line, we get this rock curve, which looks quite good. This is not so bad either. If we take the decision around here, maybe. So it works quite well with this NN interpolation. Here is also another example from another alphabet that we tested against, also with the NN interpolation. Similar results. But then when we when we processed the image from 100 pixels to 28 pixels, instead of using the nearest neighbor, we used this bilinear interpolation. And the results are very bad, actually. So even though it has learned images, which for us looks very much the same, just the difference between how the rescaling is done affects the results very much. So it's the same for both these alphabets. So it works quite well for NN interpolation, but not for this other method. Okay, so in this domain with machine learning in this functional safety domain, it's very important to know the data and understand the scope of it. So what data should the network be allowed to process, and how should the data be pre-processed. It was very important when we were doing image analysis with filters, and it's even with machine learning that is supposed to solve all problems, it's still very important to have full control of the data. And for us, it's very important to understand what is unique in the images. So here we could say that this image is not similar to this, but in a big scene, it may be also important to say not that the whole image is new or unforeseen, but maybe there are some objects that should be taken into account especially. So that we also need to look into. And what we learn also is that we can show that this method works with this simple data set. But when we go up to the high definition color images, we have to do a lot of work to understand if it works at all. And also how, I don't think that's solved either, how to compare images in this very high dimensional space. So how can we compare the input image with a new image that comes in? So estimating the distance between two such images is very difficult. Yep. Thank you.
Thank you. We do have time for questions on this interesting topic. Okay. Young and fast.
Thank you.
Yes.
Thanks very much. Extremely interesting presentation. Lots of things I'd like to ask, but can I just pick up one thing? You gave that example of the panda becoming a gibbon at the beginning.
Yeah.
How would you view your safety cage solving that problem?
So luckily this example, you need to know the exact model of your network. The network has many classes, output classes. And to be able to do this, you need to know all the training data. And then you look for such examples that are very close to the border between the gibbon and the panda. And then you try to tweak your noise to make the input image go on to the other side. So it's yes, it can happen, but it's very unlikely.
So does that mean you're effectively making the space between the different classes that you're classifying bigger? Is that in effect what's happening? You're making the distance in the n-dimensional space between the classes bigger than it would be otherwise? Is that how it works? I don't understand the intuition.
No, in this example, you just push that input over to the other side. Or you push the decision to the other side by manipulating the input. And you have to know the border there to be able to manipulate. So you cannot just, it's not by chance, it's designed to do this.
Okay, further questions? Experiences? I'm sure this is a topic which is receiving a lot of attention now, either algorithmically, training-wise, or architecture-wise. So it may also be that we have follow-ups on this topic later during this conference. We have a keynote by Håkan Simenkrona, for example, who might be touching upon related safety standard. Okay, so thanks a lot, Christopher.